All right, we're going to continue on with preparation of amines today, but we're going to be talking about reductive amination, and I'll talk a little bit about reductive amination and what that entails. But let's first start with just our generic reaction. You can take a ketone or an aldehyde, react this with catalytic acid, and ammonia, for example, remove water, and what would we get out of this? This is from our aldehyde and ketone chapter. We've got a primary amine, an imine. So in this case, we would get our imine. So this will work with either a ketone or an aldehyde. Will it work with a carboxylic acid? No. It would just deprotonate your carboxylic acid. So this really only works well with ketones or aldehydes. They're electrophilic enough. And then in the next step, we have a double bond between a carbon and a nitrogen. Why don't we reduce that down to the single bond and go to our amine? What reagents do we use to reduce a double bond down to a single bond? Think about alkenes. H2 and platinum, right? So we could do this. And this would be a reduction. You can use palladium, platinum, even nickel sometimes. But in this case, we're just reducing a double bond to a single bond. Yeah, you can reduce cyano groups using lithium aluminum hydride. But in this case, it's just a carbon-nitrogen double bond. You can reduce this with hydrogen. The interesting thing with this reaction is it does work, and this is called reductive amination. But it's not commonly seen. But it will reduce other groups on your molecule. And I'll just call this other FGs for functional groups. So it's not a very selective reaction, but it's an example of rudimentary reductive amination. So what's another method that we can reduce molecules with? Kareem was on the right track before. So why does LAH reduce things? It's a hydride source, right? So we have other methods where we can reduce molecules with hydride. And this is pretty common. But let's take a look at a difference here. Let's compare a ketone to an aminium ion, or an imine.
Dr. Engel, we did, oh, it's not a double bond. Because we did reduce, oh yeah, using LAH and H2O to the NH2. But was it a triple bond? No, it was a amine.
Okay, so now I've got a question for you guys. Let's compare a ketone to our imine or our aminium ion that we're forming. Which one's more electrophilic? Which one would prefer to accept a hydride? You can keep on saying it. It doesn't make it more, right? If you move this double bond up and delocalize it, this carbon is very, very positive, right? Much more positive than on a ketone. So imines and aminium ions are very, very electrophilic.
Are those supposed to be H's or R's?
Oh, yeah, they should be H's. Thank you. Oops, shoot. So these are more electrophilic. Shoot, what just happened? Sorry, guys. This is more electrophilic. The ketone is less electrophilic. How do we normally reduce a ketone? So LAH is kind of overkill. What's the gentler way for reducing it? Yeah, sodium borohydride can be reduced with NaBH4. This can be reduced with something that is more gentle than NaBH or NaBH4.
Why?
Even though LAH would work correctly.
LAH is like firing a cannonball into it. You don't need to do it.
However, it's very violent, however, very effective.
Okay, so what is it then? Can you be more specific than something?
What's that?
Can you be more specific?
That's what we're going to get into.
Well,
So the question is, how do we make a more gentle hydride donor?
write all that. We just come up with
Specifically, we only want to reduce the iminium group. We don't want to reduce our ketone before it forms the iminium group. So the key to this is we want something more gentle. So let me go back. So we need something more gentle than sodium borohydride, or else we're just going to reduce our ketone. And so the new hydride source we're going to see is something called sodium borohydride, but let's put this on a scale of hydride sources.
Did you just say that's, well, I thought that was the other one. Yeah. I'm confused.
So let's make a list of hydride sources, guys. All right, what's king of the hydrides? LAH.
Because it always works.
It always works, but sometimes you don't want it to always work.
Always works. There's no some cases. Always works.
So we've got lithium aluminum hydride. So that's the strongest. What's the next strongest? Sodium borohydride. Oh, that should be a sodium, not a lithium. And then the next one we have that we're going to learn about today has a cyano group replacing one of the hydrogens.
That's the weakest.
And that's the weakest. So essentially we have a scale of weak to strong. But let's try to find some rationale for why lithium aluminum hydride is stronger. Let me actually straighten this out. Why is lithium aluminum hydride going to be a better hydride source? Yeah, it's lower on the periodic table. What happens when we go down a periodic table in terms of bond strength?
You can donate the hydride a lot easier.
Yeah, let's think about this in terms of acid. What's a better acid, HF or HCl? HCl, right? You go down a column, those bonds become weaker, right? So in this case, because aluminum is a bigger atom, this is a weaker bond.
It has to do with like the size of the molecule, correct?
Has to do with the size of the atom. So aluminum in this case is bigger than boron, so it's going to be a much, much weaker bond, which correspondingly makes it a better hydride source. All right, now let's go down to sodium cyanoborohydride. Why is this going to be a weak hydride donor?
Must be a strong bond.
Think about the negative charge. It's not quite resonance. We'd be violating the octet rule if we delocalize that into the carbon. But what do we call it when something's electron withdrawing?
Electron withdrawing.
Or what can we refer to that as? Induction, right?
Said that. I just said that, Dr. Engel, and you didn't say anything.
So stabilized by induction. Oop. So sodium cyanoborohydride is a really great hydride source for reducing aminium ions, but it won't touch carbonyl groups. So let's take a look at what's going on here.
Should we write that down? What did you say? Won't touch carbonyl?
I'm going to write it down for you guys. You get no reaction. So sodium cyanoborohydride isn't a good enough hydride source to reduce a ketone or an aldehyde. What were you going to say? So let's talk about that. We'll get a list going of some of these reactions. This will reduce an aminium ion or an imine to the corresponding amine. And so what people do is they take a ketone, then they first form their aminium ion using an amine, an acid source. Oops, sorry. This should be minus H2O. I'm mixing my notes up. Yep. And you can go to your amine by reacting this with sodium cyanoborohydride. In this case, this is kind of neat because it can be done in one pot. Meaning you don't have to actually set this up as two separate reactions. What if we, like Kareem said, decided LAH is the best reagent for everything, and we just throw in LAH into this reaction in a one-pot reaction? What would immediately happen? Yeah, you would immediately reduce your ketone or aldehyde to an alcohol before you could form your aminium ion.
You hear that, Kareem?
Question. Can you explain a little more depth as to why LAH would not work in this case?
It would reduce your ketone or aldehyde before your equilibrium could occur between your aminium ion.
If you did it too hot, would it not still work?
What's that?
If you did it too hot, would it work? So theoretically, it would work.
Theoretically, but it would be much, much more work.
However, on the reaction, it would work.
On paper.
On paper, it would work. I will never actually.
So if a strong hydride source were used,
He's the one who said LAH always works.
Don't you know they lie to us in chemistry? Have you not learned that yet?
Just wait for him to say LAH might work.
it would immediately, hey guys, let's calm down. Reduce your ketone or aldehyde. So in this case, sodium cyanoborohydride is the perfect mix. It's that Goldilocks effect. You want something that's just reducing enough to reduce your aminium ion, but not so reducing that you reduce your ketone or aldehyde. All right, so this is reductive amination, but let's make a chart of what's going on here, because this is incredibly versatile and incredibly useful. Okay, so in this first example, you can react it with ammonia. Second example, you could react it with a primary amine. And third example, a secondary amine. And in each case, you can take acid and sodium cyanoborohydride. And let me get the skeletons drawn here. In this one, you can get a primary amine. This one, you can get a secondary amine. And in this one, you can get a tertiary amine. So you can use reductive amination to get to any sort of substituted amine. It's a very, very powerful mechanism. And the coolest thing about this is that it's one pot, so you don't have to deal with resetting up a reaction, purifying it, dealing with any of that stuff. You just shake and bake, get it to work. All right, so what's that? It's one step, one pot. So there's not a 1 and a 2. You just, like I said, shake and bake, and you can go straight to your amine. All right, so let's take an example of this reaction. This reaction is really, really popular in the pharmaceutical industry, and so I've got an example from the pharmaceutical industry. We'll get to that. Okay. So this is a really, really popular drug. I meant to look up how many billions of dollars it sold. So this is a precursor to the final product. The actual drug is an amine.
So what drug is this?
Just a second.
Oh, man.
Let me draw it out first.
Okay. Yeah. Are we on to the Breaking Bad yet?
We'll get to Breaking Bad.
Oh, yeah. Learn about
Okay. Does anybody know the name of this drug?
How are we going to know the name of this drug?
Hey, there's some pharmacy techs in here. I'm asking them. All right, I'll give you a hint. Billions of dollars of sales. Starts with a Z. Makes you happy. Zoloft. So this is Zoloft. And the way I have it drawn is racemic. The actual Zoloft is an antiopure at this top position up there, but reductive amination, as far as we're going to learn, isn't stereoselective. So we've got to ask ourselves, what reagents do we need in order to accomplish this transformation?
That R2NH, oh wait.
Let's give specific reagents. No R groups this time.
Methyl NH.
So methylamine.
Oh yeah, NH2. And then H plus.
And then we need acid in order to form our aminium ion. And then how are we going to reduce it without reducing our ketone first?
NH3. Yeah,
Sodium cyanoborohydride. I know we should write it NaCnBH3. That would make more sense in terms of naming it, but this is how it's written in the book, so I'm going to stick with that too. All right, let's do another one.
Now we're getting the good ones, right?
All right, you guys can't get me in trouble for this, because this is actually one in your book.
Oh, well then you're just copying the book. This is the methamphetamine.
Yes.
All right, so this is from Breaking Bad. All right. So how many of you guys have seen Breaking Bad? Do you guys remember when he refers to a P2P cook?
Yes.
Okay, so what do you think P2P could stand for? Hint? P2P. How would we name this molecule? So Walter on the show steals phenyl-2-propanone, or a lot of people call it phenylacetone. And what was the other stuff he stole out of the tanker car? Hopefully I'm not giving this away for people who haven't seen the show. Methylamine. Right? So if you take this and you steal methylamine out of your tanker car, and you treat it with an acid source, you can do it's a lot of Hollywood. All right, so this is the example they give in the book of making meth. If you actually watch the show, he uses a different reduction technique that uses mercury and aluminum. It's aluminum amalgam is what it's called, and that's what he uses on the show. People wouldn't do that because you'd have mercury contaminants in there. The other thing I will say, just to protect myself, you cannot get a hold of phenylacetone. The DEA controls all of these precursors and makes it nearly impossible for anybody to even try to attempt this synthesis. So it's a novelty to look at, but it's not something you could ever practically do, so don't dream of being Walter White. It would be a terrible idea, you'd get arrested, and you wouldn't even be able to buy the chemicals to begin with. So, what's that? You can, it gets, even the precursors to that are controlled. All of these things are controlled. So just to do venting about the DEA is so concerned about meth making that iodine is a controlled substance now. They are trying to clamp down on this because it is such an easy reaction. And so the problem is any Joe Schmo off the street can look this up off the internet and try to make it. So they try to control it as much as possible by controlling access to precursors. All right, so let's move on to something less risky. All right, guys. Let's do the synthesis for this compound.
That's impossible to make.
It is possible to make using reductive amination.
You like put the reagents in? You're missing 2 boxes.
I'm just telling you, I want you to synthesize this. It could be in one step.
One pot.
I'll let you guys try to work it out here for a second. I'll give you guys a hint too. If we go back up and we look at the example above here, we made a new bond between a nitrogen and carbon, and that used to be a carbonyl. So replace this bond with a carbonyl and you're back to your intermediate. So try to figure it out using that. So in this case, you've got a couple options, but I'll just pick one. Let's cut that bond.
So that'll be, oh.
Can you cut the other one, Spencer? Not that one, but the one below it.
We'll talk about that. All right, so let's ask ourselves, what precursor would we need? It'd be an aldehyde at that carbon. And then I'll try to keep it oriented in a way where we can kind of see where that bond is made. And there we go. And then the only thing we would need would be H+, our acid, right? So this would actually cyclize in on itself and form an enamine in this case. And then this would need... Why would we be getting an enamine in this case? What's our nitrogen source? It's a secondary amine. Secondary amines, when they add into ketones or aldehydes, become enamines. We can still do reductive amination on those because of the resonance structure that's there. Okay, so that's one route. What's another route we could use? Yeah, let's try cutting that one, and then see what the compound would look like then.
So it's like tax cycle. I learned stuff when it RP in green form. Yeah, like that. Yes.
So I'll put my hydrogen up here just to try to orient it out of the way. But you could have a really, really big cyclic system that could close in and form a bicyclic system. And again, we would need our acid source. And sodium cyanoborohydride in order to do this. No. All right, you guys ready for another more challenging one? All right, so we're going to start with this. It's going to be a multi-step synthesis. Let me move this over. There we go. All right, let's try to think about just a basic strategy here. We have a closed ring and we're going to an open ring. What's one route we can do this? Ozonolysis. So in order to do the ozonolysis route and open that ring, we first need to get a double bond there. So what do you guys think the first step should be? So what I would do is radical bromination. All right, and then if we want, we can treat this with a base. So I'm just going to use sodium methoxide.
Would any base work though?
You'd want to use a relatively non-bulky base. If it were too bulky, you would get your Hoffman product, and that wouldn't work well. So you do want to get your Zaitsev product. So you do want a small base. Then we do O3 followed by DMS, or dimethyl sulfide. Okay.
That's the part where you can use zinc and water, though, too, right?
Yep. 2, 3, 1, 2, 3, 4, 5, 6. And then what would we need for this last step? Yep, we need acid. What amine would we need?
Yeah.
Yes, dimethylamine.
Oh, because we're adding 2-methyl group C-side. Right?
Yep.
Do we need like excess or something?
So, oops, sorry, you're right. This should be a CH3, thank you. And then when you do your reductive amination, you can end up with the final product. Good catch, Abby.
Hey,
All right.
You know, I had this teacher, whenever a student corrected the teacher, they got extra credit for it. I'm serious.
Then I would be giving away points all day long. All right, so let's make a reaction flowchart. We're going to try to piece a lot of these together that we've learned today and yesterday. All right, we've got one route where we can treat this first with an alkyl halide. Followed by hydrolysis. Actually, let me change it to that. There we go. All right, so what do we call this synthesis? Yeah, the Gabriel synthesis. It was our savior from the explosive synthesis that was what? What's the one that's explosive? Azide or azide?
I know, I was here and I still don't know.
So the azide reaction is similar. You still do an alkylation on an alkyl halide. Then you can treat it with LAH, followed by water. And then the last one we had that we just learned today was you could take ammonia. You could react this with H+, followed by an aldehyde and sodium borohydride. And you can get to a primary amine. So we've got 3 routes at our disposal through which we can make a primary amine. All right. Can we use these to make secondary amines?
Sure. No, something else.
At least the Gabriel and the azide synthesis? Not very well, because those are SN2 substitution reactions. So the bulkier the groups are, the less effective it's going to be. So if we want to go from a primary amine to a secondary amine, we can again just do reductive amination, but this time use a slightly different aldehyde, so I'll do R prime there. And you can get to your secondary amine. What if we want to get to our tertiary amine? Just do it again, right? You can do reductive amination to form whatever sort of amine you want. You're not limited there. So we'll use R double prime. And we'll use an acid source. And now we've got our tertiary amine. What about if we want to get to our quaternary ammonium salt? I want to substitute this amine more. We've got lone pairs. Can we do reductive amination? Can you form an enamine or an imine with a tertiary nitrogen source? No, you cannot. So it's maybe another route to install another alkyl group off of that nitrogen.
Grignard.
Not a Grignard. We can just do normal alkylation.
Of course.
Right, because that nitrogen lone pair is a great nucleophile, so we can just react this with another alkyl halide. And so I'll call that R triple prime. Nope. And you end up with it positively charged with your X counter anion. And this would be your quaternary ammonium salt. So that's a good question. Do you think this would be stable or unstable?
It's voltage enough so that it doesn't get attacked, but it has a positive charge, so it's just like, I'm here to get attacked.
In this case, it's actually quite stable. What these are really, really popular for are phase transfer catalysts. Do you guys remember that from the reaction that we did earlier this year? We added phase transfer catalyst. All a phase transfer catalyst means is that it's something that will transport an organic soluble reagent into an aqueous layer and allow for a reaction to occur. Quaternary ammonium salts can't really make up their mind whether or not they want to be in water because they're ionic, or whether or not they want to be in an organic layer because they've got 4 alkyl groups off of them. So these are really, really nice reagents to use for phase transfer catalysts. So we got to use that during, I think it was our aerobic oxidation reaction. Was that right? It was last quarter sometime. I'm trying to remember the time we used that. So this is our general flowchart. You can use reductive amination for everything except forming your quaternary ammonium salt. Why don't we just do alkylation the whole time? So let's go back up to like this step between our primary and secondary amine. Why didn't I just toss in an alkyl halide? Yeah, exactly. Every alkyl group we add on turns that nitrogen into an even better nucleophile, and the reaction will run out of control. But by using reductive amination, we can control it a lot better than just with a generic alkyl halide. All right, I've got one last synthesis problem for us. Is it okay if I switch now? Okay, so let's go back and do one last synthesis problem.
Dr. Randall?
Yep.
For the Gabriel synthesis, you wrote acid for your second step. Isn't it the hydrosome?
You can use hydrazine or acid. Hydrazine is oftentimes preferred, but your book shows acid a lot. And sapling may show acid too.
Okay.
Yeah. Either will work. The key is you need to hydrolyze that amide bond and release your amine out. You can use other carbon sources, obviously.
I would hope so. Otherwise, or you can look at it wrong.
There are actually a couple different ways to do this reaction. All right, raise your hand if you think you've got it on paper. All right, a couple people. I'll give you guys one more minute to work on this, and then we'll do it as a class.
Dr. Engel nominated me for the most annoying thing. I don't know Kareem might be
All right, I think that's a good time to continue on with the synthesis. Let's start with ammonia. What reagents would we need in order to make an intermediate? I'm just going to choose cyclohexanone. let me get this inside my brackets. H plus, and then NaBH3CN. What would we call this? Cyclohexylamine. So we go from cyclohexanone to cyclohexylamine. Now we need to get to our final product. What was that?
Is it 4 hexanone? Or something?
Yeah. So 2, 4, 6, 7 carbons. The carbonyl should be on position 4, so this would be 4-heptanone. And then we can do reductive amination again. And we can get to our final product. What would be an alternate route?
Can you start with the ketone and then use NH3 with the acid? And
Yeah, there's a huge number of different ways to do this. You could start with this ketone in place of the cyclohexanone, and then just switch the order of reactions. That would work equally as well. So oftentimes with these reductive aminations, you do have a lot of options available to you. It's not that one's more right than the other. All right, so let's go back a little bit to last chapter. It was chapter 19, I guess, with the reactivity of amines. We talked a little bit about acylation. What's an acyl group?
Tastes like aldehyde, but instead of a hydrogen, it's an aldehyde.
Yeah, so this is an acyl group. We saw this during our synthesis of Tylenol, right? What reagent can we use, or what reagents can we use?
What defines that as an acyl group?
It's just a carbonyl. It's a methyl ketone coming off of a nitrogen, or really anything for that matter.
So, like, a methyl ketone coming off anything?
Yeah, it will be referred to as an acyl group. Yeah. So what do we need in order to get an acyl group installed onto aniline?
It's like acyl chloride.
Yeah, you could use. Whoop, sorry. You could use an acid chloride, right? Or alternatively, we could use an anhydride as well. The acid chloride is going to be the most reactive reagent here, so we can just throw that out there. And the question is, why would we want to do this?
Good question.
It has some unique utilities that we didn't talk about. So let's say we want to brominate the para position of an aniline. What reagents would we need? Yeah, iron tribromide or aluminum tribromide, really any sort of Lewis acid. Why might this not work very well?
We might get ortho.
Yeah, exactly. We've got a super, super strong activator. So in fact, you don't observe this. Instead, what you get is the overbrominated aniline.
Should be in both spots.
Yeah, it would be both ortho and para because that aniline is just too strong. It's going to activate all the positions. So the workaround is to acylate it. And then we can brominate it. Is that acylated aniline going to be an orthopara or metadirector? It's going to be orthopara. It's a weak activator. Because that carbonyl is not attached directly onto the ring, so So we can get our bromine installed there. And then, if we want, we can try to get back to our para-aniline. And how would we remove the acyl group? It's just an amide. How can we hydrolyze an amide? Acid, right? So you just need acid in order to hydrolyze an amide bond. So in this case, all you can do is use that acyl group as a temporary protecting group to essentially deactivate your aniline and then hydrolyze it off, and you're straight back to your aniline without the problem of overbromation. All right, I think that's where we're going to leave it today. When we come back on Monday, we'll go over the remaining reactivity reactions with nitrogen. A lot of it's going to be review, though.
I would say, how much of Monday is going to be reviewed?
It'll look very similar to reactions we've seen. Oh, shoot. Sorry, we do have a test on Tuesday. So, sorry, Monday will be review for the exam, and then Wednesday we'll continue on. Sorry.
Will everything finish after that?